Hello everyone. It is pretty late now, so it's the perfect time to talk about GPUs. Today I'll be talking about GPU stack and architecture, and I will talk about it from the perspective of someone who understands the traditional computer architecture. And so I will motivate why GPU is even relevant in the first place and how we can motivate its stack and architecture respectively. Um, I'll just go right into it. So to understand GPU, the classically we have to understand what CPU is doing. So both GPU and CPU are chips. CPU is the more traditional one. Let me just illustrate it with an example, right? So let's say nowadays, we program things on computers, right? Let's say I write a C++ program. Well, I need the computer to understand what my C++ program is doing. So in the stack, there is a middleman called a compiler, right? This compiler will take in my C++ program and output a stream of bits. So you can think of it as 0101, 0110, a stream of zeros and ones. The machine will interpret this as perhaps one instruction, perhaps the next 8 bits as another instruction. And this is passed to the CPU. A CPU is just some integrated circuit. I won't draw the full thing, but when people talk about the CPU, usually they are referring to the core. A CPU is a chip, so it has a lot of things, right? It has input-output interfaces, it has memory controller, but most of the time people are talking about the core. The core is the piece of component on the CPU that takes in these instructions and executes it. So to talk about the core, let me just use the RISC-V core as an example. I am using RISC-V because my school taught it in RISC-V. And I also think it is a good example to talk about. So what does a core actually do, right? The RISC-V core, you can think of it as 5 logical stages. I'll just write out the stages here. Firstly, we have the instruction fetch stage. Then we have the instruction decode stage. Then we have the execute stage. Then we have the memory stage. And lastly, we have the write back stage. But let's just suppose we have some instruction 00011011, for example. In the instruction fetch stage, it is exactly as what it is doing in English, right? It is fetching the instruction from somewhere. So when the compiler compiles this C++ program into bits, these bits must be stored somewhere. And usually they are stored in memory. For instruction fetch, sometimes we fetch the instruction from what we call the I cache. So this cache, even though I wrote the dollar symbol here, the cache is actually this cache. Basically, it is a storage place for the instructions. So we need to fetch the instruction from somewhere. For example, this maybe 8 bits is an instruction, right? So it fetches the instruction from some place. Then the core has to decode what that instruction is. It has to pass what these 8 bits mean. So this is in the instruction decode stage. So the instruction decode stage, just as an example, it will take in groups of these bits. For example, maybe this 01 means an index 1, right? This 10 means index 2, right? 10 in binary means 2. So maybe it's talking about index 2. And this 11 refers to index 3. And this 00 perhaps means, for example, add. So I'm just using an example here, okay? Maybe these 8 bits encode the instruction add x1, x2, x3. In register transfer level, you can think of it as first take the register value indexed by x2, add the register value indexed by x3, you sum the result because it is an add instruction, and you put it in the register indexed by x1, right? You overwrite whatever value is present in the register x1. Typically over here in the instruction decode stage, we have a component called the register file. The register file, you can think of it as another storage place. So this register file typically has 32 registers. Each registers are usually 32 bits. So you can think of it as R something, where this something can range from x0 all the way to x31, right? 32 registers. So this addition instruction is just saying, take the value in the register indexed by x3, take the value in the register indexed by x2, add them together because it is an add instruction, and put the results into the register indexed by x1. Then in the execute stage, usually we have something called the arithmetic logic unit or the ALU. So you fetched the value of the registers at x indexed by x2 and x3 respectively. You can now put those two registers, so for example, Rx2 and Rx3 inside the input to the ALU. You can think of this ALU as approximately a function that takes in two inputs, x1 and x2, and spits out a value y. This ALU can do a lot of things. So this f can be a lot of things. It can be addition, it can be subtraction, left shift, right shift, multiply, I think is also possible. XOR, also possible. That's why it is called arithmetic logic unit, because it implements a lot of arithmetic operations. And then it will have the resultant value. So note that I don't write over here Rx1 because it is not stored back to the register yet. That happens in the write back stage. Okay. We have a fourth stage called memory. This memory is a bit disjoint, but not entirely from execute. Addition is only one type of instructions. There can be a lot of other instructions. For example, a memory instruction is load word, where you want to load value from memory into the register file. Then you'll use load word, for example, x2, 0, x4, which means you want to load the value of the memory at address x4 plus 0. 0 is this offset. You want to load this into the register indexed by x2. For example, the register file is a place of storage, but registers are very quick to access because it is on chip. Memory can be somewhere off the chip. It takes longer to access a particular cell in the memory. If we can have infinite registers, we will store everything in the register file, but we don't have that because of physical limitations. That's why sometimes we have to store values to memory and get values out from it, which is why there is this memory stage. So typically we interact with something called a D cache or just the memory itself, SRAM, DRAM. For clarity, I will do something like this, right? And finally, in the write back stage, we want to write a value back into the register files. We have computed the value of Rx2 plus Rx3. We will write it back to the register file through a write port in the register file. So these are the 5 logical stages of a RISC-V core. The reason why I want to show it is because it really has a lot of overlaps with the actual GPU core. So if we understand this well, we will understand what GPU is trying to do very easily. And I think just as a note, typically, computer architects think of this as 2 separate partitions. We call everything before the execute stage front end. And we call everything after the execute stage back end. This is similar to web development in some sense, but front end is a place where instructions get fetched and decoded, and the back end is where the actual computation happens, right? Like at the execute stage, at the memory and write back. We will talk more about this in a section later on. Another thing that I want to talk about here is what is the problem that CPU is trying to solve? Problem that CPU solves. And I'll just write it down first. It is to minimize latency. So what is latency here? This is the 5 logical stages of a RISC-V core. So what happens is an instruction will go into the first stage. And once it has reached the 5th stage, the instruction is considered fully executed. So you can imagine this is the time taken to execute one instruction. So as an example, right, let's say I wrote a program that has 10 million instructions, right? That's 10 to the power of 7. That means to execute my program, 10 to the power of 7 instructions must pass through this pipeline. If every instruction takes about 10 nanoseconds, right, to pass through the pipeline, 10 nanoseconds is 10 to the power of minus 8. Then my program will execute in 0.1 seconds. My point is, if some computer architect managed to lower this second number by a factor of 10. So if some computer architect managed to create a pipeline such that an instruction only takes 1 nanosecond to pass through, then my program will run in 0.01 second. Basically, you make all the programs in the world run faster by 10 times. And that is great. You save everyone a lot of time given the sheer number of programs that are run in today's world, right? So computer architects or CPU cores are actually trying to solve this minimizing latency problem. which is the time it takes for an instruction to get from one end to the other, which means for an instruction to be fully executed. I think this is a good overview of CPUs. So now we will move on to GPUs. What problem is the GPU trying to solve? And I'll just write it out here for clarity that the problem it is trying to solve is to maximize what we call throughput. And I will give two examples if just to make it more fun, right? So, this G in GPU stands for graphics. So it has its roots in graphics processing. Uh, let's suppose you're playing a game, right? Let me just draw a screen over here. Let's say you're playing a punching game. So this is me and this is my opponent. If my opponent tries to punch me, let's say throws me a punch, I want this to be rendered on my screen really quickly, right? Because I want to dodge it. So where is GPU used over here? Each pixel, right? You can imagine each pixel on your screen is actually executing a series of instructions, right? They are trying to calculate what should be rendered at that pixel, what color should it be, etc. So they are all executing the same instruction because presumably the logic of each of them are the same to try to find out what their respective pixel values are. So number one, the workload has the same instructions and you want them to be executed relatively quickly, right? Because we want this punch to be rendered really quickly so that I can dodge it. And the third thing, we want them to be executed almost together in some sense. For example, if someone is throwing a punch at me, it wouldn't help me if the top left pixel gets rendered super fast. I will still not know there's a punch coming. So we want them to be relatively together. I don't know what is a better way of phrasing this phrase. Basically, all the pixels, I want them to be rendered at the same time, right? I want my whole screen to update at the same time. So this is what we call as maximizing throughput. This is what we refer to as maximizing throughput. Throughput is typically, you can think of it as the number of operations per second. If you imagine each pixel rendering to be one operation, basically this is saying you want there to be a lot of operations done per second, and that is great. If a lot of operations are being done per second, then it is basically saying your screen is rendered very fast at the same time. Another example that is pretty important in today's workload is matrix multiplication, right? Let's suppose I have a square matrix A. I want to multiply it with a square matrix B and I get some resultant matrix, which is also going to be square, that is C. Matrix multiplication is a very common problem. The thing about matrix multiplication is, or even computer science, right? As computer scientists, we always look at this type of problem and we think about it. Can we solve it by solving smaller sub-problems? This is something called dynamic programming. In matrix multiplication, we can, right? This is very common. So in math, there is such a thing called block matrix multiplication, which is you treat each of these matrices as small sub-matrices, right? Let me just denote this by A11, A12. The first index always denotes a row. The second index denotes a column. B11, B12, B21, B22. And I'll just label two of them for now. You can just think of each smaller subblock as just an element and it works out similarly. So basically for C11, I can write it out as A11 matrix multiplied by B11 plus A12 matrix multiplied by B21. Essentially, you're doing matrix multiplication, treating each of these as an element instead, right? So A11 multiplied by B11, A12 multiplied by B21. Similarly, you can write out the equation for C12. Let me just try to get it right. Yep, I got it right. So you can write out a similar equation for C12. So notice what is nice about this, right? We are doing a matrix multiplication on two smaller matrices, smaller by exactly half in both dimensions. We are performing more of such problems and we need them to be performed at relatively the same time, right? It doesn't make sense if you calculate this matrix multiplication and then you have to wait for a long time or wait to do this matrix multiplication sequentially because ideally you want to accumulate them pretty fast. you can imagine, right, for each of these subblocks, you can further divide them into smaller subblocks. And you'll just get a lot of repeated problem. You can think of all of them as one operation, and you want to basically do a lot of those operations at a relatively quick speed, and you want to do them almost in some sense together because you need to accumulate them at this point. This again goes back to the typical workload that GPUs are meant to handle. And as one of my professor usually say, when a new problem arises, when the problem changes by a bit, then new technology will follow. And this is exactly why GPU came about. So I will talk a bit about GPU for now. Okay, sorry. I just want to talk about another thing. So these two are different problems. And I think the very classical analogy that people use to explain this is minimizing latency. You can think of it as when you want to buy a car, you want to buy a very fast car because it takes you very short time to travel from point A to B, right? You're minimizing latency in some sense, the time it takes for you to travel from point A to B. Then let's suppose now you have a group of friends, let's say 20 people. Now it's going to be a problem because your car can't possibly take 20 people. It can only take, let's say, two people. Suppose you bought a very small car. Then if you want to bring all 20 people from point A to point B, you need to make a lot of round trips, right? And that is presumably worse than if you just cater a bus to carry all the 20 people over. So this is why, technologies like cars and buses both coexist. It's like people spend decades trying to optimize cars to make them fast, but buses are still going to have a place in today's world because of this difference in the problem, right? You can imagine if you use a super fast CPU to render your screen, what will happen? Well, yeah, so your top left pixel is going to get rendered really fast. Your second top left pixel is going to get rendered very fast. And then you'll see your screen basically render in a bit of a cascading manner, right? It will just render from left to right, starting from the top. And that's going to mess up your game experience. You want them to be executed relatively quickly. It doesn't have to be all super fast, but you want them to be executed relatively quickly and relatively together. So that is why GPU's workload is different. Okay, enough about motivation. So let's talk about the GPU stack, finally. So GPU stack. The reason why I talked about the CPU stack is because there's a lot of parallels, right? So I have a computer now. And let's suppose I have a machine learning workload. Let's say maybe I have a matrix multiplication like the above that I want to offload to a GPU. My computer doesn't have access to a GPU core. So the next best thing is, okay, maybe I just buy a GPU. I connect it to my computer through a cable of some sort. So just to get our terminologies right, our computer is what we will call the host. And the GPU, because it is, you can think of it like a thumb drive, right? It is a device. And this is host, this is device. Great. And now suppose I write a C++ program, right? Again, I need to have a middleman called a compiler. But this compiler now has an additional job, right? It takes in a C++ program. It must do something for both the host and the device because something is going to get run on the device. It's meaning to say it must compute two sets of machine code or two executables. So firstly, it will compile something to be executed on the host side and something to be done on the device side. Furthermore, like how does a compiler even do this if we give it a normal C++ program? So something has to be changed with respect to this programming language itself as well. And I think at this point, it is better if I just switch to a code environment just to show you guys what I'm talking about. So let's look at, oh man, it's too late at night. Let's look at, yeah, let's look at my terminal, I guess. So over here, I have spawned up a Docker instance and look what we have. So, oh, we have a CUDA script over here. So let's just take a look. So let's open it up in Vim, right? Okay, this is just a very naive CUDA program that I wrote just for the sake of understanding how GPUs work, right? So, it is just a normal C++ program. Well, the first glaring thing that you can see is, well, there's this function qualifier global here. Function qualifiers are pretty common in CUDA programs. This global just denotes that this function vector add is a kernel. A kernel is equivalent to a function, honestly. So it's just saying this vector add is a kernel that is supposed to be compiled and executed on the device. And also, the host can initiate the launch of this kernel. Basically, back to this diagram, it's telling this compiler that I have this vector add kernel, and you should compile it on the device, but give the host a handle to call this to launch this kernel. Okay, let me switch back. And vector add, this function is not very sophisticated. It is just saying, okay, I take in the start pointers of these two arrays A and B, and I want to store the result of the addition in this array with pointer C. I will go through the body of this function later, and because it will make more sense. So firstly, we have n. N is the number of elements in the array that we want to do our vector addition. It is like the length of the vector, right? Then we allocate 3 pointers on the host side. So things that starts with h underscore means these variables are on the host. We initialize the two arrays, and then we declare 3 pointers, but we don't initialize them yet. We declare 3 pointers that are meant to denote the address of the arrays A, B, and C on the device. And then we call cuda malloc. Malloc just stands for memory allocate. So we allocate memory for these 3 arrays on the device side. So note that these 3 pointers only make sense when we want to get something on the device, right? If we address them on the host, we'll probably get rubbish because they don't refer to anything on the host. They are meant to point to an address location on the device. Then we have memory copy. So one thing to note here is in this model, let's say we have some variable called host A on the host, and we want the data to be available on the device. We must do a mem copy, which is copying the memory of whatever is stored in host A to an address on the device. So in this case, it's DA. That's why we differentiate them with the prefix H and D for host and device. So we are doing a memory copy here to copy over the 2 input vectors. And CUDA makes you specify your intent, which is great, right? You are making sure you want to mem copy from host to device. Then this is the interesting part. Firstly, we have threads per block, and then we have blocks per grid. Basically, I mean, this third line makes it pretty apparent what we are trying to do. We are trying to launch the kernel vector add. The kernel is what we have seen here. The global function qualifiers hints that it is a kernel. We launch this kernel with this number of blocks, whatever this number is, this number of blocks, and each block will have 256 threads. So remember what the workload of GPU is, right? It has a lot of the same operations. So we want to spawn a thread to do each individual one of them. And a block, for now, you can think of it as just a logical group of threads. So it is just saying you want this number of blocks times this number of threads to do the work of vector addition. And you're passing the 3 variables over here. These variables are all addresses on the device. And now you can understand what this kernel is trying to do. Basically, each thread will have a unique I over here. This I is determined by which block it belongs to and what is its thread index in that block. And then it is only going to do the work for that particular element or for that particular I. Each thread only does one addition. And if you are a lucky thread, well, lucky or unlucky, depending on what's your life philosophy. So if your I is, let's say, greater or equal to n, then you don't have to add anything because there is simply not enough element for you to add. So you'll just be an idle thread. You will not even pass into this body condition of this if branch. Then after we launch this kernel launch is asynchronous, meaning when you launch this kernel, you'll just immediately run the next line. However, the next line, which is a mem copy, is synchronous, which means by calling this function, you'll wait for this kernel to finish processing on the device side, which is good because this mem copy is basically saying, okay, assuming that your result is complete, you want to copy over the memory on the device side, which stores the result back to the host, right? You're trying to copy from device to host. And by calling this, you're assuming that the result has been computed. And this is exactly the case because this line is synchronous. Synchronous meaning it will wait for the kernel to finish executing before it initiates the mem copy, which is great, right? It's great for our case. And then finally, you do a check. There's nothing interesting here. And basically, at the end, you must free the memory on the device and you must also free the memory on the host. Great. So we have went through this program. What's next? So now you have the C++ program. You want to compile it. So this is the reason why I spawned up the Docker instance because this Docker actually has the compiler. So the compiler is called nvcc. It's called NVIDIA CUDA compiler. And we check that we can have it over here. Um, to compile the program, firstly, okay, I'll talk a bit about compiler now. So this compiler, right, compiles the C++ program to the device and the host. But the compiler must be aware of the architecture, right? This device, this GPU, it has an architecture. NVIDIA made so many GPUs now. Each of the GPU has some unique name, some unique number. The compiler must be aware of the architecture because the machine code that it generates must be interpretable by the underlying machine or the underlying architecture. So I will use SM90 as the underlying architecture. SM probably stands for streaming multiprocessor, but honestly, it is just a name. So I will just do it. nvcc, so we compile it with an architecture that is SM90. I also want to keep all the intermediate compiler files just to see what it is doing. And then we give it our CUDA C++ program. And this will take a few seconds. And now we can look at our directory. So there's suddenly a lot of stuff, right? Because these are all the intermediate files that nvcc uses because I specified this keep flag. And you see, because we compiled it with the architecture SM90, right? All the final products like this cubing means CUDA binary. So it's saying this CUDA binary is compiled specifically for the architecture SM90. And this is going to be a binary. We can take a look at it later. This fat binary is basically saying, okay, this executable can run on multiple different architectures. So basically, fat binary is a very portable executable. It can probably run on SM90, SM80, etc. And this presumably has a larger size than the CUDA binary. Some other interesting files over here is this PTX file. So I will take a look at what the PTX file has. So this is the PTX file. Let me go back. So I still want to talk a bit about the compiler. So for now, right, our impression is that a compiler takes a program written in some programming language like C++ and converts it into something that the machine understands, which is some machine interpretable code, like bits of zeros and ones, right? That is one of its function, which I won't write down because that's a long sentence. The second function it has to do is to perform optimization. So remember, right, the compiler basically dictates how many instructions there are in your resultant machine program. If the compiler is smart, let's say, for an inexperienced programmer, suppose just as a pseudocode, int x equal to 0, and let's say an inexperienced programmer wants to add 5 to it. Well, one way of adding 5 to it is just to do a for loop and you just add 1 to x, right? Suppose someone codes up something like this. The compiler is going to look at it and be like, the person is just going to add 5 to x. So the compiler can basically do a code generation that is equivalent to add x5, something like this. This is not correct in RISC-V, but I'm just trying to give an example. The compiler can reduce this whole code into just one line by its process of optimization. Otherwise, what will happen over here? Well, this for loop is going to execute 5 times, and each of these for loop has a branch condition, right? It needs to check for this condition. So there's going to be a branch instruction. It has an increment instruction. It has another increment instruction. So this is going to take at least 5 times 3 instructions. In fact, if you do n here instead of 5, this will take you 5n instructions. That's linear in the number of times you want to do this for loop. But the compiler basically just condenses it into one instruction, which is great, right? We want there to be less instructions. How does the compiler do optimization over here? Well, the compiler, usually it takes in the C++ program. It won't immediately convert it into machine code because the machine code is already architecturally dependent, right? So the final state is machine code. And this is architecturally dependent. What does architecturally dependent mean? Architecturally dependent means in your underlying chip, your chip can be very special, right? All the people at NVIDIA probably thought up of a lot of small tricks and a lot of small operations to be placed on the chip. If your compiler has awareness of those type of operations, your compilers can use those type of operations to do more optimizations, right? So this optimization over here is already architecturally dependent. Basically, by knowing what the architecture is, you're already going to make some architecturally dependent optimization. But before we reach that stage, we probably want to keep all the optimization architecturally independent. So in the middle, there is this thing called intermediate language. I hope I got this right. Intermediate language is not architecturally dependent. It is architecturally independent. And the reason for that is if you convert something from C++ into intermediate language, you can do a lot of optimization in itself. It's basically a bag of tricks. You can do global optimization, local optimization, people optimization, all the optimization things you will learn in a compilers class. You keep it architecturally independent. And now, if you want to compile it to an actual machine code, all you need to do is to convert from this intermediate language into machine code. Let's say you suddenly upgrade all the chips on your server for some reason, right? You can just start off from this intermediate language and you do compile to, let's say, SM80, for example. This you compile to SM90. So it makes it very portable as well, right? So for two reasons, one is optimization, and maybe the third one is called portability. That is why usually we have this intermediate language. And for just to make it clear, in CUDA, right, nvcc is the compiler. And this intermediate language is what we call PTX. And this machine code is what we call SASS or streaming assembly. I have no idea what PTX stands for, and I'm okay with not knowing that for now. So this PTX file is interesting. So if we are looking at it right now. Yes, it is generated by nvcc. So you can take a look at this, right? The target is SM90 because we have said that it is SM90, but nowhere does it actually use the fact that it's SM90, I think. Let me just pull out the program so that we can look at it side by side. Right? Remember, this is our original kernel, right? It takes in a few parameters, 1, 2, 3, 4. The first two are constant float pointers, which means they are addresses, which is why they are all 64 bits because each address has a size of 64. The last one is 32 bits because it is an integer. So all these are understandable. This sequence of instruction is essentially doing this I computation, right? I is equal to the block index times the block dimension plus the thread index. So the block index is this CTA ID. This is because in NVIDIA's original architecture paper, they call a block a cooperative thread array, which is CTA. I, I don't know. I think a block is a better terminology, to be honest. So this is the block index. This is the block dimension, right? It is the number of threads. And then finally, you have the thread index. You do a multiply and add operation on all three. That's how you get your I. And this set P means set predicate, right? It is testing greater equal. So this R1 register stores the I. It is testing whether R1 is greater than R2. What is R2? R2 is N, right? So if I is greater or equal to N, we are going to set this predicate bit. So this predicate bit is just probably 1 bit, a Boolean bit. And if this predicate bit is true, then we will proceed to jump to this label. What is this label? Well, this label just returns. And this is correct, right? If I is greater or equal to N, then we don't want to do anything. That is great. Otherwise, we go into the following set of instructions. This CVTA stands for convert address. It converts an address to global. So global just means the memory of the GPU. In GPU, the memory is called global memory and it is stored somewhere off the chip. And I will remember to talk about it during the architecture later. But like this is interesting, right? Because there is a reason why in the intermediate language we want to do a convert to global is because we are not sure at the intermediate language level how these functions are going to be implemented. So this instruction in particular convert to global. We are not sure how this is going to be implemented. So at the intermediate language level, it is okay to have this pseudo instruction which leaves the actual compilation to sass to do. Then percentage %R represents a 32-bit register, percentage %RD represents a 64-bit register, and this mul is just multiplying by 4 because all the floats are going to be 32 bits. So to jump by an index of I, you need to multiply it by 4. We do an add to add it to the offset of A. We do the same for B. So basically, this gets AI and BI. And this final add is just adding AI and BI together. And finally, we need to find the address of C to store to, and we finally store to the global memory, F32, to the address of CI. Yeah, I think like reviewing this is very interesting. What else do we have? Well, we have the it will be interesting to see the sass. So what we can do is we call nv disassembly and we try to run this assembly on this cuda binary file. Okay, I think let me just bring it out a bit. And whoa, there's a lot of things. I think I'm looking for this, right? So we have a vector add kernel over here. These set of instructions correspond to the first set of instructions that we reviewed just now, which is really saying this is loading the thread ID, this is loading the block ID, and we are getting I in register 9 over here. And then afterward, this second set of instruction corresponds to what we talked about earlier, which is the actual loading AI, BI, and then storing the result into CI. I mean, you can just match this with the PTX instruction that we went through just now. This is a bunch of loads. You do F add over here. This is adding AI and BI. AI and BI are these R4 and R3 that you have obtained somewhere above, and then you store the result to R9. Then finally, you need to persist the result, the value in the register into global memory, right? And this is storing wherever that place is. Yeah, otherwise, this is almost the same as PTX. So yes, we went through this entire pipeline. I hope that was interesting. And now I can finally talk about architecture. Phew, I never thought I would make this far, but how do I motivate the GPU architecture? So let's review the workload of GPU again, right? We have a lot of the same instruction or a lot of the same operations, and the operations are the same because they are executing the same instructions. We want to make sure they are relatively fast, and we want to make sure they are relatively simultaneous. Okay, so these are the three properties of a GPU workload. So how do we design an architecture that satisfies these three properties? And this is after knowing how a kernel launch works, right? So let me review that as well. To launch a kernel, basically we have to call the kernel name, so something called vector add, right? We use the triple angular bracket. We can supply 4 arguments here actually, but in the code just now we only see 2, and that is fine. Only the first 2 is really required. So firstly, we have the number of blocks, right? The number of blocks. You can think of a block as a group of threads. We have the number of threads per block. And then there are 2 more arguments. I can briefly talk about them. The first one is how much shared memory are you going to dynamically use in your kernel? This is relevant later on. I'll talk about it when the time comes. And this is the stream, the CUDA stream. By default, we use stream 0, but there can be other streams. A stream is really something related to synchronization, but I won't talk about it in this video. Maybe in some future video. So this is how we launch a kernel. Essentially, you can think of it as every time you launch a kernel, the kernel will give you a couple of blocks, right? Let's say 3 blocks, and each block has a number of threads. Let's say you launch some other kernel, let's say matrix multiply. You can launch it with the same syntax of parameters, and its blocks can be different, right? Its blocks can be larger. it can have more threads per block because it is an entirely different kernel from the first one, right? It is denoting that it is a different operation, right? If you think about each of these threads executing the same operations, each of these threads in the first row executing the same operations, each thread in the second row will be executing a different set of operations than the threads in the first row, right? They are only executing the same instructions within the same kernel. For example, you may have something like this. Let me just move on to a new page to draw the GPU architecture now that we have reviewed some of the things above. So let me just use a very big space and I call this my GPU. And I have my host somewhere here with a wire connected to GPU. Okay, so how do you want to do this? The host, it can launch kernels. So let me just draw in the few blocks from earlier. And it can have some pretty big blocks, right? Suppose you launch a different kernel. How is our GPU going to handle the receiving of these blocks? Well, this is exactly like in real life. Someone give you a lot of tasks. Let's suppose you're a manager of a team, right? How are you going to, handle all these tasks? Well, you're going to schedule them, right, to some of your workers. So similarly, there's going to be a global scheduler in GPU. No surprise here. There's this thing called a global scheduler. So now this is where I explain what a block really is. A block, so let me just write it at the top. A block is a unit of scheduling at the global scheduler level. So it is a unit of scheduling at the global scheduler level, right? So this global scheduler will take in these blocks and look at the blocks like, oh, okay, let me assign this to something. All right, let me assign this block to something. Let me assign this block to something. The global scheduler will never partition the blocks and assign like a sub block, right? It will always schedule using blocks as the basic unit of scheduling. So what does the global scheduler schedule to? Well, it is going to schedule to workers, and the workers in the GPU context are called streaming multiprocessors. So let me just write it here, streaming multiprocessor. And I'm going to just write SM for the rest because, it's a long word. Sorry, let me just complete my picture. There can be more streaming multiprocessors. So this global scheduler will say something like, okay, streaming multiprocessor one, right? Let me give you a block. So it gives it a block. Streaming multiprocessor two, let me give you a block. Streaming multiprocessor three, let me give you a big block. It schedules things on a block level. Um, but is its job really that easy? I will talk more about it later on. So now let me talk a bit about streaming multiprocessor. So a streaming multiprocessor, you should really think of it as really similar or analogous to a core in CPU. And why is it analogous? Because it has almost the same components, and I'm going to draw them for you, right? So firstly, it has something called sorry, that's a very poor rectangle. It has something called the L1 I cache. Remember I cache? That's the cache to get instructions from. It happens in the instruction fetch stage, right, of the CPU core, of the RISC-V core. So L1 I cache. What's the reason for this? Well, all the blocks, streaming multiprocessor receives blocks from the global scheduler, right? All the threads in the same block are going to execute the same instructions. So it makes sense to have a L1 I cache over here, right? It is to hold the instructions closer to where it will be executed. So you have L1 I cache over here. Similar to a core in CPU, there is this thing called a register file. You see this in the instruction decode stage. Register file. Streaming multiprocessors has a lot of registers. I think the one that I saw has 2 to the power of 14 registers. It has an abundance of registers and it is shared across its multiple lanes that I'll talk about later on. It has, a lot of lanes which are execution unit. I will talk about them later on because I want to finish some discussion on global schedulers first. So it has a lot of lanes, right? So I'll put lane 1, lane 2, lane 3. And, finally it has this thing called, let me just remove it for a bit. It has this thing called shared memory. And this is exactly like the memory in the RISC-V core. So you can really see that a streaming multiprocessor is really analogous to a core in a CPU, right? It has the iCache, the register file, a couple of execution units, and the shared memory. Like, what else do you want? Like, the write back is implicit over here. Okay, so um, now I want to shift gears back to this global scheduler because you might be thinking its job is really easy. You just distribute work, but it is actually not that easy, right? Okay, it is exactly like in real life. Let's suppose you're the team leader of a talented team, right? You have, let's say, 4 workers for you. If you are a scheduler, right, do you schedule all the work to be given to one person, right? Probably not. Like the worker will either be exhausted or very unhappy at you, and that's not good. Um, do you schedule tasks in a round robin fashion, meaning the first block or the first work goes to the first worker, the second work goes to the second worker, and so on? You might think that is fair, but these blocks are different. It's like saying you give person one a difficult task, person two a easy task, person three a easy task, person four a easy task, and what if coincidentally your task five is a hard task, and you give person one another difficult task? That worker will probably be unhappy as well. So this global scheduler needs to be concerned with more things than just randomly scheduling things, right? He has to be aware of, you know, the number of registers in each register file. So for example, streaming multiprocessor one, let's suppose it has already allocated, six of its register file. It has very small amount of registers left. Then it cannot get a block with a large number of threads, for example. It also needs to be aware of shared memory or the space remaining in shared memory. This is a very neat thing. Sorry, I don't think I should write in blue again because it is too light, but shared memory is entirely programmer controlled, which means the global scheduler controlled program shared memory is programmer controlled, which means global scheduler at the time of kernel launch knows exactly how much shared memory is going to be allocated per block, right? So in summary, you can think of this global scheduler as solving a resource constrained scheduling problem. So let me just write that down. Resource constrained scheduling problem. Scheduling problem, right? It is essentially saying, okay, I am aware of all my workers. I know how much resources they have, right? How much registers they have left, unallocated, how much shared memory they have left. And depending on those and how much my blocks require, I'm going to schedule that block to the first available streaming multiprocessor. And I think that really makes sense in real life, right? It's like let's say you're a team leader, you also need to be aware of how much task each worker has on their plate and how much time they have per day, etc. So I think if you're good at real life, you'll be a very good computer architect. uh, what else do I want to say? So that's all I want to say about the global scheduler. So let's move on to a streaming multiprocessor, right? I have talked about why we need the L1 iCache because all the threads in the same block will execute the same instructions. So it makes sense to have a level of memory hierarchy that is just in each streaming multiprocessor, just like in a regular CPU core. We also talk about why there needs to be a register file. So something I want to talk about here is all the registers in the register file are thread private, meaning to say each thread will be allocated its own set of registers, and that is private to that thread. Oh, I didn't explain threads, but threads you can think of them as a single stream of execution. So essentially, they execute instructions one by one. Each thread needs a couple of registers to store their temporary values. So you can think of it as a short-term memory or a working pad for the threads. Then I will talk about lanes soon, and I think we know why shared memory needs to be in place because you can't store everything in your register file. Your register file is like your short-term memory or a working pad, right? You use it to do some quick mental math, but if you want to do something more complicated, you probably need to load or store things from the shared memory. So now let me talk about the execution lanes. But before I talk about execution lanes, I need to talk about something. So I want to keep my GPU diagram separate. So I'll start off over here. I want to talk about something called the vector architecture. So now remember just now we talked about the front end and the back end of the RISC-V core. So instruction fetch, instruction decode, execute, memory, and write back. Right? We talked about how everything before the execute stage is regarded as the front end of the architecture. Everything after the execute stage is regarded as the back end of the architecture. So now the problem over here, for a GPU workload, all the instructions are the same. So another related problem is, let's suppose I have two arrays, right? Let's say an array A, say 1, 3, 5, 7, 9, 11, dot, dot, dot. And I have an array B, let's say 2, 3, 5, 7, 11, dot, dot, dot. And I want to add array A and B together. So let me just be consistent and treat all of them as having 6 units. I want to add A and B together, right? In a RISC-V core, how would I do that? Well, I'm going to do something like load word. I'm going to load the first number from A. I'm going to load the first number of B. I'm going to add the first number and the second number together. And I need to store the result to C. Let's say C is the result array, right? So you see, to add two numbers together, I need to execute 4 instructions. But what if I want to add both arrays together, component-wise? Well, I'm going to execute 4 instructions times however number of elements in the array. That's 4 times n, where n is the number of elements that I want to add. That is a ridiculous amount of instruction for something that can be described so simply, right? So computer architects have thought up of this vector architecture to basically execute less number of instructions. What if there's an instruction called v-add, vector add, that just takes 2 vectors, v1 and v2, 2 vector registers, v1 and v2, and add them together to v3? Well, to the back end, the number of operations will be exactly the same. It still needs to perform n operations, n add operations, right? Back end still performs n add operations, but the front end only need to fetch 1 instruction and decode 1 instruction. That is great. That lowers the pressure on the front end. So let me just write it here. So basically for the front end, 1 instruction. That is great. It decreases the pressure on the front end. How do you decrease the pressure for the back end so that the back end doesn't become that much of a bottleneck? Why not just have more execution units, right? You can have multiple execution units. So each of these execution units, again, you should think of it as an ALU. And there can be multiple different execution units, right? For example, you can have like a FPU, floating point unit, to do floating point operations if the instruction is a floating point operation. You can also have some special function unit. Special function unit, maybe it computes cosine, sine, exponential, etc. What you're doing over here is you already decrease the pressure on the front end. You also want to decrease the pressure on the back end so that the back end is not that much of a bottleneck. And to do that, you just increase the number of execution units, right? So let's say you have n add operations. If your add operations can only use ALU, then if you have 2 ALU backend units, then n over 2 operations go through each one, right? Presumably in this, n over 2 clock cycles, the instruction will be completed. I hope that makes sense. This is exactly like in real life. So if you ever took an airplane before, you'll realize when you land, right, you have to go through the custom or the immigration checkpoint or something. And there are several queues, right? There are probably 2 queues for residents. There's 1 queue for maybe international visitors, 1 queue for diplomat. It's exactly like that, right? If you have a lot of operations coming, you either open up more queues or you just keep it the same way. But basically, what I'm trying to say is people will filter themselves based on those queues depending on what type they want. And it is exactly the same here, right? The instructions come over, something over here called the scoreboard will say, okay, I look at this instruction, what type of units will it use? Does it use arithmetic units, in which case it goes to the ALUs, normal ALUs. If it requires floating point units, okay, I'm going to assign you to the floating point execution unit. If you need to use special function unit, I assign you to special function unit. If there's already something executing on the special function unit, you need to wait for a while first, right? This is exactly the same as in the airplane queues example that I just talked about. So let me just use blue here. Sorry about that. We call each of these backend execution units and the component after lanes because it makes sense. They are all queues or lanes. And this is the vector architecture. Something I also want to mention over here is vector architecture is trying to solve this paradigm, right? Single instruction. You take a single instruction, hopefully a single vector instruction, and because of that instruction, you operate on multiple data, right? This is precisely what is going on in this example. You have a single vector instruction and you are going to execute on so many data, and these data are all independent of each other, right? You are adding independent data. So vector architecture is trying to solve this SIMD paradigm. Our GPU, sorry, our GPU is trying to solve the SIMT paradigm. Single instruction, multiple, T stands for threads, right? This is like what we have motivated earlier. The workload of GPU is really saying, okay, we have a lot of similar operations. All these operations will execute the same instructions, and this corresponds to threads, right? Threads is like a thread is a single execution stream. It executes that stream of instructions, and all those streams are the same. Basically, you want to use one single instruction to start off multiple threads doing the same work, if that makes sense. We'll see how that works in the execution lanes, right? So let me go back to the GPU diagram. And let me use this site SM2 to illustrate what a lane looks like. So I'm going to magnify this lane tree and I'll show you what a lane looks like. Let me see. Okay, so let's suppose the global scheduler schedules two blocks to streaming multiprocessor one, okay? A small block and a big block. Because the global scheduler schedules things in the units of blocks. Okay, let's look at what goes on in a lane. So firstly, the first component that I want to talk about is this thing called warp scheduler. So don't be afraid, right? This is the final level of scheduling that I'm going to talk about. There's only two schedulers in a GPU. One is the global scheduler and one is the warp scheduler. The warp scheduler is the second level of scheduling. So the global scheduler schedules things in units of blocks. This warp scheduler is trying to select things based on warps. So that's why it's called a warp scheduler. So a warp, let me just try to define it here. A warp, you can think of it as a group of 32 threads. And these 32 threads must be from the same block. So let me just write from the same block. Okay, so we scheduled let's say in streaming multiprocessor one, we scheduled two blocks. Each block can be split up into a number of warps, right? Because a warp is 32 threads. So in the CUDA code that we saw just now, each block has 256 threads. So, well, if you do the division, that's about 8, right? 8 warps per block. So basically, once the global scheduler passes blocks to the streaming multiprocessor, the streaming multiprocessor can view those blocks in terms of warps already. Each block should have an integer number of warps. I think that is the convention. If you try something different, let me know how the result goes. A warp, let me also write over here, is the unit of is the unit of execution. So when things get executed in this lane, so this is a lane, right? It is an execution unit. It executes one warp at a time. So it executes 32 threads at a time. These 32 threads, you should really think of it. Okay, let me just draw somewhere over here. So let's say I have 32 threads. These 32 threads, sorry, it's very hard to pronounce. These 32 threads in the same warp, you should think of them as executing in the same locked step, meaning they are actually progressing through their instruction stream at the same pace, right? They are all executing the same instructions because they come from the same block, but they are going to execute them at the same pace, meaning all of them execute one instruction at a time, right? They progress through in lock steps. Meanwhile, in the same block, there may be other warps. So let's say this is warp 2. The threads in warp 1 will execute in the same lockstep. The threads in warp 2 will execute in the same lockstep. But it is not guaranteed that threads in warp 1 and threads in warp 2 will execute at the same lockstep. Basically, the warp scheduler will swap warps in and out. So threads in warp 1 may progress faster than threads in warp 2 or vice versa. This is why warps is the unit of execution. So we have warp scheduler. This warp scheduler basically selects which warp it wants to execute based on whether a warp is available to be executed. I will talk more about it later. So this picks a warp, picks a warp to execute. And there's a lot of lanes out here. So each of these lanes really has a warp scheduler. And this is why warp scheduler selects things because, if you have multiple lanes, let's say you have multiple workers, you don't want them to select the same task to do, right? You don't need 3 workers to do the same task. You want them to select different tasks. So this warp scheduler in different lanes will presumably select different warps to execute on. So we have the warp scheduler. I think that's all I want to say for warp scheduler. Then we have this thing called the iCache. Sorry, the L0 iCache. And this is because all the threads in the same warp will execute the same instruction in lockstep. So it makes sense to pull those instructions into this cache early on so that future retrieval of the instructions that this warp is going to execute will be fast, right? It makes sense to have a higher level of memory hierarchy in this place. After this L0 iCache, we have expectedly the execution units. So for example, we have int32 execution units, and we'll have a lot of these, right? Because we have 32 threads in a warp. So every single instruction is going to generate around 32 units of work. So we have a lot of int32 units out here. It's usually maybe 8, 16, or 32, depending on your architecture. We also have a lot of FP32 units because, now for matrix multiplication, all the elements are floating points. So you have a lot of FP32 units. You have a lot of FP64 units if you want more precision in your floating points. You have your special functional unit for computing sine, cosine, exponential, whatever. And you have your tensor cores. So something I want to say over here is that all of these, so let me just write, all of these are called cores, but they are actually analogous to the CPU cores ALU, the execution unit in the CPU core. So I think the core over here is pretty misleading, but that's what NVIDIA calls it, so we are sticking with it. The next thing I want to talk about is, what does CUDA even mean? So CUDA means Compute Unified Device Architecture. So I know that, from a history point of view, it is called Compute Unified because it kind of unifies the graphics engines execution units into this pipeline by expressing it in simple execution units such as integer execution unit, etc. But I think, to me at least, I think the beauty of GPU is that you have all these execution units in one place, and it just depends on what instruction the warp is going to execute next. This lane will choose the correct execution unit to schedule the work on. So essentially, it is just like the vector architecture. You have a lot of execution units in your backend, and using one single instruction the warp of 32 threads will all execute the same instruction. So one instruction will generate 32 units of work, and these 32 units of work will be queued in some selection of this sea of execution units to be executed. And I think this is really beautiful. What else do I want to talk about over here? Well, I want to talk a bit about the tensor core. So what is a tensor core? Let me just move on to this space. So what is a tensor core? This is the core that actually executes your matrix multiplication, right? Because that's an important workload for machine learning and for a lot of CUDA computation anyways. So executes matrix multiplication fast, or relatively fast, I should say relatively fast. I'm pretty sure if people want to make a really fast matrix multiplication by itself, people can make it faster. But if we want to crunch a lot of matrix multiplication, then I think GPU is probably the way to go. So what is a tensor core? Tensor core, I think of it as a systolic array architecture. So what is a systolic array? Well, a systolic array is a spatial architecture where you have a lot of processing units. So all these circles, right, you can think of them as processing units. Processing elements. Yes, that is right. So P is, right, you can think of them as processing elements. So let me just draw. And they are spatial architecture because they are trying to solve a specific problem that is matrix multiplication. So what happens in a matrix multiplication, right? Let's say I've a matrix A multiplied by a matrix B. I'll just make it simple. I'll write it in the row form A1 dot, A2 dot, A3 dot, and A4 dot, right? And I have my matrix B, I'll write it in the column format. B dot 1, B dot 2, B dot 3, and B dot 4, right? So matrix multiplication is essentially doing this, right? You use the row of A1 dot multiplied by the column of B dot 1, that generates you a number, right? Because this is literally a row vector multiplied by a column vector. It should give you a scalar. And this gives you A1 dot dot B dot 1. And similarly, you can write, sorry, let me just write transpose here for clarity. So A1 dot transpose B dot 1, right? And similarly, it gives you the rest of the numbers. But my point over here is, let's suppose you want to compute matrix multiplication. To compute the numbers, if you do it by this naive way, you're reading the first row of A, you're going to read in the columns of B one by one to get the first row of the resulting matrix, right? So let me just complete it. Right, you're going to read in the first row of A, and you're going to read in the whole matrix B just to get the first row of the resultant matrix. Then what are you going to do? You're going to read in the second row of A, and then you're going to read in the whole matrix B again. But that's redundant, right? You're reading in B multiple times. Can you read B just once and get the result of this matrix multiplication? It turns out that you can with this spatial architecture. So in particular, let's consider this idea, right? We stream in the values of the first row of A1 dot, A1 dot. Let's stream in the first row of this spatial architecture. Let's stream in A2 dot in the second row, A3 dot in the third row, and A4 dot in the fourth row. But we stagger it, right? We stagger it such that we stream in the first row first, we wait for 1 unit of time, so let's say a bubble, and then we stream in the second row of A in the second row. And then for the third row, we need to bubble it 2 times. And for the fourth row, we bubble it 3 times respectively. We do the same for the columns of B, right? Of course, we need to remember the bubbles. Let's say I'll use this for bubbles. And you see what will happen over here. When we stream in the elements of A1 dot and B dot 1, well, the first node, what does it see? You will see the elements of A1 dot and B dot 1 coming at the same time. Like the corresponding elements that need to be multiplied together will come in at the same time, right? If we keep on streaming the values in, right? You'll see the first element in that row and the first element of in that column, multiply them together, accumulate it somewhere, and in the next time step or the next clock cycle, it's going to see the second element of A and the second element of B. It will multiply that, accumulate it together with the first value of accumulation, and you will just proceed on with this. If you repeat this logic for the other processing elements, you'll realize all of them will compute exactly the values at the resultant matrix. All this processing unit needs is just 1 times accumulator to accumulate the value of the multiplication or the products. And you just need 1 times multiplication unit. So all the processing units can be really simple. And with this, you only need to read in both matrix once. And you have the value of the resultant matrix. You perhaps just need to stream out the values of the resultant matrix one more time, right? But this is effectively a good call to compute matrix multiplication for small matrices, which is exactly what GPU needs, because GPU can break down the matrix multiplication problem into smaller sub-problems, which are multiplication of the small matrices, and then you use this tensor call. Amazing. So we did tensor calls. Wow. And that's really about it, right? This is the lane of the GPU. So again, right, global scheduler schedules in units of blocks. Once it comes to the streaming multiprocessor, the streaming multiprocessor will see those blocks as warps instead, because it's no longer useful to see them as blocks, right? The scheduling has been done. Then the warp scheduler in each of these lanes will choose a respective warp that is available to execute to be executed. So another thing that I want to talk about over here is, why is GPU relatively fast? And how can it get so much work done per unit time? Well, I just want to note here that GPU has low cost of context switching or switching between warps. So what is context switching? Well, in CPU, we also have multi-threading, the concept of multi-threading. And the purpose of multi-threading is really when one thread hits a long latency operation. For example, one thread says, okay, I need to fetch something from memory. Well, fetching something from memory takes very long, maybe hundreds or thousands of clock cycles, depending on your architecture, right? Meaning to say, when a thread is fetching things from memory, 1,000 arithmetic operations can execute during that time, right? So one way for CPUs to deal with it is this concept of multi-threading, right? Only one thread can be resident on a core at once. Resident meaning, okay, let me just write it down. So a thread, right, is a single stream of execution. Meaning it's just executing instructions after instructions. It has some execution context. So execution context is like the states that you need to execute instructions. For example, imagine yourself as a thread. You have a list of instructions, but you need to know where in the list you're at, right? So that's a program counter. So program counter is an execution state. You also need your working memory, like what have you done before? So that's your registers in your register files, etc. Right? You need some execution context. So a thread is resident on a core if the core has the PC and the execution context in it. And if you want to switch a thread out, well, definitely you need to load in the execution context of the next thread. And that may take an amount of time, right? Because you need to load in all the registers that the next thread is going to use into the register file, for example. In GPU, that's not a concern. So again, remember the unit of execution in a GPU is a warp. So when a warp hits a long latency instruction, such as loading something from memory or storing something to memory, the whole warp can be switched out for another warp. And this is okay, or it doesn't take that much long time, because you see we have the register file at this juncture of the streaming multiprocessor, which means all the registers of all the threads of all the blocks scheduled to this streaming multiprocessor is already resident in the register file. So it takes very little time to get out the execution context of the next warp, meaning the next warp can start executing almost immediately after being switched in. I hope that makes sense. Otherwise, you can always listen a few more times. Um, yeah, so one final thing I want to talk about is the memory. So we have this global memory that I don't have enough space to draw, but we have this global memory, or we call it the GPU RAM, right? This is also called the GPU RAM. Basically, or this GPU chip, it has shared memory. It is controlled by the programmer. And it is a bit problematic because what if some of the registers actually needs to write something to memory to retrieve later on? You can't really just write it to shared memory because this is something that's supposed to be programmer controlled. So imagine, right? Let's say a register has spilled over, right? You need to write the value of that register to memory. If you write it to shared memory, then it means that the program can arbitrarily increase the memory allocated in shared memory, which means that the global scheduler does not have a good view on how much shared memory is left per streaming multiprocessor because the program can change that. So this will affect the job that the global scheduler is doing, which is the resource constraint scheduling problem. So the solution is really, if you really have a register spillover, right? If your program really needs to write something to memory in the process of its execution, you write it to the global memory. And this is costly because the global memory is located somewhere off chip. I think we usually use the high bandwidth memory technology over here, right? But basically it's located off chip, it's located somewhere near the GPU, but not on the GPU. So it takes time to store things to it and load things from it. I just want to point that out because I think it is just to distinguish it from the shared memory. I will note here, however, that there is also a portion of the memory that is called the data cache over here, and that the program can actually use. The shared memory and the D cache are the same component, but it is partitioned very well in the sense that the programmer can allocate the portion that is the shared memory, and whatever is in the D cache is something that is dependent on the architecture or how the program is being run. Yeah, I think that's all I want to talk about over here. So let me just give a quick summary. So in summary, we first talk about the CPU. Because looking back, CPU and GPU really has a lot of similar things in common. We talk about how the CPU core is analogous to the streaming multiprocessor in GPU. We talk about how the ALU unit is analogous to the execution units, or what we call the cores in the lanes. We talk about the problem that CPU and GPU are trying to solve, right? This is to minimize latency. This is to maximize throughput. I gave pretty illustrative examples for those, so I hope that's enlightening. Then thirdly, we went through the GPU stack. It is the same as the CPU stack. We write a C++ program, we go through a compiler, we finally compile it on the host and the device. And we talk about how the compiler over here is the nvcc, how there's an intermediate language called PTX, and how the executable is called sass. And we also look at the CUDA programming model over here, which is the code. And then finally we talk about the GPU architecture, which is very interesting, right? We motivated why it is like that, because to start off, you need something to schedule the task, you need the components of a CPU, and you need execution units. So we compared it with the vector architecture. We also see how the tensor cores are like the systolic array architecture. And I think that's pretty much it. We also talk about the concept of warps and blocks, right? Blocks are the unit of scheduling, and warps are the unit of execution. And I think that's about it for GPU. I'm pretty happy that I finished talking about all of this because I think it's very hard to talk for a long period of time. But I think with this, I feel ready to move on to more advanced things in GPU. And I hope this is enlightening. Yeah. See you the next time.